Hi, everyone. The next topic is model selection or variable selection. So how can we choose the best set of linear predictors out of many candidates of predictors? So think about that we have 10 possible predictors, x1 to x10. And we would like to explain why by sum of x1 to x10. Maybe x1 and x7 and x10 have sufficient information and other variables are not relevant to y. So we have to identify the method to have x1 and x7 and x10 as the best set of predictors. And the biggest difficulty is if we choose a larger model always achieves a smaller residual sum of squares. Okay, so suppose the true model is x1 and x7 and x10. So the y is equal to beta naught plus beta 1 x1 plus beta 7 x10, 7 plus beta 10 x10. But if we include x1 to x10, everything, I just put everything, then actually the error gets smaller for our data set. Because more predictors, that means basically more variables, so we can explain more, maybe just by chance. So RSS cannot be the criterion to choose the best model, because always it chooses a best model, even though that we don't have any true relationship between y and x2, for example. And there are two common methods to evaluate the model for forecasting, to be exact, for test performance. Okay, so we have 100 observations and we fit the model, but finally we want to see if that model applies for new data set. So that test performance is more important. So how to evaluate that test performance? We have two methods. So one is the cross-validation. So this is more common method these days because it's theoretically much easier, just computer intensive, but now computer is very strong, so it's very popular method. So cross-validation, the idea is divide the data set into k subsets. Suppose k is just a number, so for example, 3 subsets. And use k-1 subsets to fit the data, so fit the regression model, then evaluate the residual sum of square in the other subset. So say we have the subset ABC, so then we fit the linear regression with subset A and B. So then we get coefficients. And we use those coefficients to make a prediction for the data set C. Then we evaluate the residual sum of squares. So that basically mimics the situation of test performance. So we have only the 2/3 of data first to fit the data, fit the regression model. Then we use the other 1/3 to evaluate the performance. But that performance largely depends on how to choose A, B, and C, how to separate the data set. So just to be fair, that we do the other ways. So we use data set A and subset A and C to fit the data. Then we evaluate the error size, residual sum of square, with using data set B. And finally, we use data B and C to fit the data. Then we evaluate with the data set A. So then we take the total residual sum of squares. Then we can get some reasonable evaluation of the test error size. And the other way is Akaike information criterion. So this is actually quicker way for simpler models. So and actually we minimize the slightly different function than residual sum of squares. So we choose the model which minimize this quantity AIC. That is -2 times log of likelihood function plus 2p. So likelihood function we have already studied. So for each model, we can calculate likelihood. And we multiply and take logarithm and multiply by -2. So negative of something times some function of likelihood. So actually the smaller value is better. Larger likelihood is better. So that means the smaller -2 times log of likelihood is better. So smaller value is better. Smaller AIC is better. But we have another term, 2p. Here, p is the number of predictors. So if we have more predictors, actually AIC gets larger. So it basically balances between likelihood and the model size. The smaller model is better, but at the same time, the smaller likelihood or smaller sum of squares are better. So log likelihood is almost sum of squares in linear model. So this is easier for a linear model, but sometimes for more complicated models, the AIC cannot be calculated. And theoretically, it's guaranteed that the AIC, I mean, the predictors chosen by AIC basically are kind of converge to the true model. Sorry, the maximum prediction power model. So the AIC is basically the best method to choose the model for out of sample prediction or forecasting. And here is an example. So we are still using the Georgia ballot data. And I have already loaded that one. And we defined the percentage of Gore already. And we use the weighted least square method. And remember that this one, okay, summary of this. So you can see that okay, so percentage of African American, this is very significant predictor to explain the undercount, but the percentage for Gore is a little bit vague. So negative 0.95 is somewhat different from 0, but not far away. So we want to see if this model is better than just a model with percentage of African American. We can compare AIC to get this. Okay, so I compared these three models, the model with just intercept and model with percentage of African American as a predictor, and the model with percentage of African American and the percentage for Gore. So we compare these three models and we calculate AIC. So if we have linear model object, the capital AIC parenthesis, the name of the model, gives the AIC. So we have these AIC values, which is smallest. Actually, the center one is smallest. So this is the best model in terms of out of sample prediction. So if we have maybe some other counties not included in the data sets, then which model to apply to estimate the percentage of undercount, then actually the percentage of African American only. So this is better model than this L mod 2. So difference is not that large. So basically, if we have one more useless predictor, then AIC gets worse by 2, gets larger but by 2. So yeah, so the difference is 1. So it's a kind of, you know, a kind of the vague situation. So yeah, actually the slightly this AIC is better, but not better, not much better. So that's the conclusion. Okay, so we have more ways to use AIC. Generally, we have a larger model with 10 predictor, say. Then we want to drop more and more variables to get the optimal predictor. So think about the true model. I mean, the best model is X1 and X10 and X7 and X10. only 3 variables are important to y. So in such a case, we can start with the model with all predictors, then we can drop one by one to make AIC smaller. So we can use the step function to implement that. So if we run step of this largest model, then we get this output. So at first, the R tries to drop the percentage of Gore, then actually AIC gets smaller. And if we drop the percentage for African American, then actually AIC gets larger, so we shouldn't drop it. Yeah. It sounds that these AIC values are not really consistent each other. Start is AIC 295. Yeah, so AIC has some normalization term. So depending on the detailed definition, sometimes it reports the different values. So previously we have 600 something, but this time we have 295. Probably we have just different constant to calculate AIC. Maybe we just multiplied by 1/2 on everything or something. Okay, so percentage of African American, percentage of Gore, if we drop, then model gets better. Then next, we drop the percentage of African American also. That is a bad idea. AIC gets worse, much worse. Gets worse by 30. So we shouldn't drop it. So at this point, we can decide that this model undercount on percentage of African American is the best model. So if we have many predictors, this is very useful method. So also this is pretty efficient because suppose we have the 30 predictors. Actually, this is the real situation when I was working in a bank, and one boss suggested to test the 30 predictors to predict inflation rate. And actually, but the 30, so all combinations, if we think about all combinations of the 30 variables, all subsets of 30 variables, we have basically 0.5 billion combinations, and we cannot really check it. But if we drop one by one, we start with the full model and we drop one by one, we have to have only 30 steps. In each step, we may drop the one of those variables. So maybe each step we try 30 different models, but the 30 times 30 is only 900. It's much better than 0.5 billion. So so this is why this step function is useful in practice to choose the best model. Of course, we cannot sometimes achieve the best model, just drop one variable at a time. So sometimes we miss the best combination and we achieve a kind of local maximum. But often this method leads to reasonably good model. And some options, yeah, actually we can start with the smallest model and add one variable at a time. Or we can specify the smallest model and largest model, and we can start with any model in between, and we add a variable or delete variable at a time to achieve some kind of the locally best model. So AIC method works in this way. So this is the end of the chapter 1, if I don't change mind later.